Okay, so welcome everybody. We start our lecture number 4, and I decided finally that it will be totally about the compactness. So we discuss this tema today, and we finish this tema today, this topic, and then next week we start with something new. Okay, so what we have done last time? Last time we have discussed this theorem 212. We are in the setting of metric spaces. We have a metric space, and then the following conditions are equivalent. A set K is compact in the metric space X if and only if every infinite subset of K has a limit point in K, every sequence of elements from K possesses a subsequence converging in K, or K is totally bounded and complete. In particular, if the metric space we are living in, if this metric space is complete, then this is the formula, what is the compact set in a complete metric space. So a set is compact if and only if it is totally bounded and closed. And last time there was a kind of question about completeness and closeness, so this is not the same thing. So that's why we have a remark 212, about closeness and completeness and relations between them. So first of all, closeness, this is a feature which is defined in a general setting of topological spaces, and it depends on the larger space the set is embedded in. So it can happen that a set is closed in one space, but not in another. Example will come in a minute. Concerning the completeness. So completeness, this is the notion which is working only in metric spaces, and it is an intrinsic property of the set itself. It does not depend on any external ambient space. So a set can be closed without being complete, but if a set is complete, it must be closed. So this is the relations between these two things, closeness and completeness, and let me illustrate it with the example. So let us consider this interval as a metric space with standard metric. And when we consider this set, so this set as a subset of X is closed because X without A is just interval from 1/3 to 2/3. This is an open set here. Yeah, so a complement of an open set is a closed set. So this is a guy, this set is closed in X, but not here in a bigger space. And obviously this set is not complete because there, for example, this Cauchy sequence, which does not converge in this set. Okay, so this is the illustration for this statement that a set can be closed in one space but not in another. And let us justify that if a set is complete, then it must be closed. So actually, if a set is complete, it contains all its limit points. There, the limits of all Cauchy sequences, and hence the set is closed. Because the closure of a set is just exactly the set itself plus all its limit points. Are there now some questions concerning these two notions, closeness and completeness? Okay, seemingly no. Thanks for the feedback. And let us go for some small remark that, so let X be a Hausdorff space with a topology tau. A subset of X is called relatively compact if its closure is compact. Sometimes instead of saying relatively compact, people say pre-compact. So in particular, in metric spaces, this is the same. Or different authors use different terminology, but relatively compact or pre-compact, this is about this statement. So if X is a complete metric space, then due to this statement, the space, this set is relatively compact if and only if this set is bounded. Yeah, we remember that last time we discussed that if a set is totally bounded, then its closure is also totally bounded. So with the same epsilon net. So everything is fine here, and we can go further. So yes, as I said, so the definition of a compact set is that any open cover possesses a finite subcover. But of course, if you are given a set, it is not possible to check if it is compact or not using this definition. So one needs really practical criterion how to check if a set is compact. So my aim today is just to discuss some criteria in different spaces. Okay, and we start with the space small L2. And the criteria looks as follows. So a set K is compact in this space L2 if and only if it is closed, bounded, and the following holds. So from now on, we discuss only metric spaces. That is, we are allowed to use this or this. But usually we will use complete metric spaces, so we are able to use this criteria. And in the case of L2 space, small L2, so the criterion looks as follows. So closed and bounded and something else to guarantee total boundedness of the set. This is exercise for you to prove this, but this is just a technical and not difficult proof. You just having this, you are able to create an epsilon net for any epsilon, just because this allows you to throw away infinitely many coordinates starting from some point, and for first finitely many coordinates, you know how to create an epsilon net, as we have discussed already last time. And you also, we have also discussed two examples. So we have discussed that a unit ball is not, so even a closed unit ball is not compact in this space. And there was also a Hilbert cube, which is compact in L2. You can check that for a closed unit ball, this criteria is not satisfied. And for a Hilbert cube, this criteria is satisfied. So you may feel what's going on here. But as I said, this allows you to control all coordinates starting from any any fixed one. Okay, so this is an exercise, and let us go further. And so the very important criterion of compactness is in the space of continuous functions on K, where K is a compact. And this is the well-known Arcelà-Ascali theorem, which is always discussed either in functional analysis or in mathematical analysis course. But it is really important, so we have to discuss it. So theorem, compactness criterion in CK. So a set K, so we consider this case. So we consider continuous functions defined on the segment from A to B, endowed with supremum norm. So the metric which is generated by supremum norm here. So for example, here it is written the distance between F and 0 in this supremum norm distance. So a set K, a subset of the space of continuous functions with this supremum norm. A set is compact if and only if this set is closed, the set is bounded. What does mean bounded? It means that K is a subset of some ball with centrum 0 and some radius r. And this means in this space that there exists. No, my radius is C. This means that there exists some C which plays the role of radius such that the distance between all elements of our set K 2, 0 is smaller than R. So this is the distance in the sense of this metric. And so closed, bounded, and something else which guarantees that in total, we have a totally bounded set. So this is the so-called equicontinuity. So a set K is equicontinuous if and only if for any epsilon there exists delta such that for all functions, so for all elements of this set, and for all points of our domain of definition, so interval from A to B, satisfying the condition that the distance between points is smaller than delta, we have this condition. This means that, okay, we know that on each segment, any continuous function is uniformly continuous. So if there would be no this thing, so just this is what is called uniform continuity. So the function f is uniform continuous on this interval AB. But equicontinuity of a family means that all elements of this family, they are equally uniformly continuous. That is, we have the same epsilon, for each epsilon, we have the same delta, not only for all points of the interval with this condition, but also for all elements of this family. So uniform continuity, which is equal for all elements, for all functions of our set. Okay, so this is the statement of Arcellas-Cayley theorem. Analogous statement holds also for more general case, continuous functions defined on a compact, where we have a metric compact, that is a compact set in some metric space. And yes, my plan is to prove this theorem because it is not that very difficult and somehow instructive. So let us start. But yeah, before we start the proof, some example. So a kind of a basic type of compact sets in this space. So let L be strictly positive and fixed. Consider the following set. It's a set of functions which are continuous on this segment from A to B, and such that we control the starting point. For example, let's say that all functions start at 0, and we control, for example, so all functions are Lipschitz, and we control this Lipschitz constant, so it is bounded by some fixed L. So then this set is closed, bounded, and equicontinuous. This is an exercise, and hence, if you show this, you get, due to this theorem, that this set is compact. So it's a typical compact set in this space. Again, this is an exercise, so I hope there will be no problem. It's just a pure technical, but not that hard exercise. Okay, so let us prove now the theorem. So let us show in first this direction. So we assume that the set is compact, a given set K is compact. And we have to show that these three items are satisfied. So first of all, if a set is compact, then the set is closed. This is by proposition 2,4, which we have proved last time. Moreover, it is totally bounded. Yeah, so now we use this theorem 212 just in the very beginning. Yes, so if K is compact, then it is totally bounded and closed. So this implication we assume compactness, so we have this. So the set is closed, so this is already done, and totally bounded. And we know that if a set is totally bounded, then it follows then that set is bounded. So this is also satisfied. So these two things are satisfied. So now our task is to prove that this third thing, equicontinuity, is satisfied. So how to do it? Let us prove it. So once again, we do in this direction. We know that the set is totally bounded. That is, for each epsilon, we can create an epsilon net. So let us do it. So take fix epsilon positive. So let phi1, etc., phi n. It's a subset, it's a finite subset of our space, CAB, with the standard supremum norm, so metric generated by the supremum norm. So let this finite set be an epsilon over 3 net for the set K. Yes, since we assume that K is compact, hence totally bounded, hence for every epsilon, we can construct an epsilon net or epsilon over 3 net for this set. Since each function phi I from 1 till n is continuous on this interval a, b, so it's a closed interval, hence each function is also uniformly continuous, uniform continuous. So since it is so, there exists delta 1, etc., delta n positive, such that, so we just write down the condition of uniform continuity for each function phi I with its own delta I. That phi I of x prime minus phi I of x2 primes, this is smaller or equal, this is enough for us, epsilon over 3 for any x prime, x2 prime in this interval, satisfying the condition that distance between x prime and x2 prime is smaller than delta I. So once again, this is a uniform continuity of each function phi from this epsilon net. But since we have finitely many functions in this net, we can find the smallest delta. So let delta be the minimum. Minimum over all delta I from 1 till n. So finitely many. Hence, with this delta, all functions phi I satisfy this inequality for any 2 points satisfying this condition with delta. Okay. Oops. I have pressed something wrong. Okay. Next step, for each element f of our set K, compact set K, choose phi I from our net such that distance between f and phi I is smaller than epsilon over 3. So this is possible because this is epsilon over 3 net for our set K. So then we have for all x prime, x2 prime from this interval. So I will wait a few seconds and then I go to the next slide because here I have no place anymore. But I hope that you have your own copy of these notes so you can just continue writing. So may I go further? Okay. Nobody complains. So I hope that yes, I go next. So then we have for all 2 points with the property that distance between these 2 points is smaller than delta. So this the minimum of all deltas. So what do we have? We have that the distance between f of x prime minus f of x2 primes. So now we use the so-called dry epsilon argument. So this is small or equal f of x prime minus phi I of x prime. Absolute value is closed. Then the next absolute value here, phi I of x prime minus phi I of x2 prime. And then a next absolute value, and here phi I of x2 prime minus f of x2 prime. And then this all is smaller than epsilon over 3 plus epsilon over 3 plus epsilon over 3, which is epsilon. Okay, so this is smaller than epsilon over 3 because phi is an element of our net, epsilon over 3 net, This is the closest element to F from this net. In a similar way, so this is also smaller than epsilon over 3 because of the same reason. And this is just the uniform continuity of this function phi I with this delta. Okay, this is a standard.
Actually,
Yes.
we can write a supremum before the first modulus and the third one. Yeah. So and then this distance supremum form will be less than 3 epsilon.
So we have written what we need. Yes, so this is what we
Yeah,
want.
everything is okay. I'm just like elaborating on one more step because like F is an epsilon over 3 net with the supremum norm. Yeah, so
Yes.
if we write the supremum,
This
then
means
this.
that for any point it is true. In particular, for this point,
Yeah.
yes. Yes, but it's just a repetition of the argument, which is a standard argumentation, which is called dry epsilon argumentation or arguments. I don't know. Yes, which is it's a standard argument of mathematical analysis. But I hope it is sometimes it is convenient to repeat such standard things. So what we have shown, we have shown. So once again, we have taken epsilon. Then we take any f of our k. We have constructed delta. We have taken epsilon, we have constructed delta, and for such that for any f and for any 2 points satisfying this condition, we have finally that this is smaller than epsilon. So that is exactly what is written here. That is, we have shown the equicontinuity. So in this direction, everything is proved. Agree? Okay, perfect. Then we now show the opposite direction. So this direction. So we assume that 1, 2, 3 are fulfilled, and we show that this set is compact. Okay, how to show that the set is compact? No, we are not going to show that from any open cover we can find a finite subcover. What we have this. So it is enough to show that the set K is totally bounded, having all this. Then closed and totally bounded in a complete metric space means that the set is compact. So let me write it down. Enough to show that K is totally bounded. Yeah, totally bounded plus closed in the complete metric space means compact. So in order to show that the set K is totally bounded, it is enough to construct a net, epsilon net for any epsilon. So let us do it. So fix any epsilon positive. So we know that the K is bounded. So let us use it. Since K is bounded, there exists some constant C positive, such that the set this set K is a subset of a ball with radius C and centrum in 0. This means that supremum over all x in this interval from A to B, absolute value of f of x is smaller or equal to C for any f in K. So we have it. It is actually written here, but okay, I have written it once again. So we remember this C. Since K is equicontinuous, there exists a delta positive such that f of x prime minus f of x2 prime this distance between them, absolute value, is smaller than epsilon over 5 for any x prime x2 prime in this interval AB, satisfying the condition that absolute value x prime minus x2 prime is smaller than delta. And this holds for all f in K. So let me call let me call it, for example, condition. So this mark. Okay, so we have it since K is equicontinuous. Now let us use it. So we are going to construct epsilon net. We do it as follows. Let x0 be equal to A, then smaller than x1, smaller than, etc., smaller than xn, which is equal to B. So we consider a partition. So B a partition of the segment AB with mesh delta. That is, this means that maximum over all I from 1 till n, absolute value xi minus 1 is smaller than delta. So we construct a partition of the interval AB. Moreover, let y0 be equal to minus c, smaller than y1, smaller than, etc., smaller than ym, which is equal to c. So let this be a partition of the intersegment from minus c to c of mesh epsilon over 5. So let me write it down nicer. Epsilon over 5. Then the statement is as follows. For each element f of our set K exists a continuous piecewise linear function. Let me call this function phi with nodes in points so points of the form xk, yl, where xk is taken from this partition and yl is an element of this partition. So there exists a continuous piecewise linear function with nodes in such points, such that, and we will write it down in the next slide, such that what happens. But I guess you already understand. So these are the elements of my epsilon net. And as soon as we go to the next slide, there will be a picture how such phi looks like. So are you finished with writing? Twice in. So may I go further to the next slide?
Yes, yes.
Okay. So this is the picture. So we have the K, it is closed, bounded, so it is bounded by C, so we have this C, which is a This is a ball of radius c with centrum in 0. Yeah, due to equicontinuity, we have also this. So we have this partition, which we have clarified on this partition. So now we have a lattice here, a lattice of interval of a compact set AB times minus CC. We have a lattice, and we consider so any continuous function f element of our set K, and then the closest guy to this f, which is a piecewise linear with nodes in this lattice. Looks like this. So what happens? So we have finished that for each f, there exists a piecewise linear function phi with nodes in these points, such that such that wait a minute, f of xk minus phi of xk is smaller than epsilon over 5, and this happens for all k from 1 till n. That is, we control the distance between function and f and phi only in these points of partition. Okay, agree?
Yes.
Yes.
Okay. Now from this property, this red property, we have the following. We have that absolute value phi of xk minus phi of xk minus 1 is smaller or equal. Again, dry epsilon argumentation, phi of xk minus f of xk plus f of xk minus f of xk minus 1 plus f of xk minus 1 minus phi of xk minus 1. So the statement is that this is smaller than 3 epsilon over 5. Let us check it. So this is by construction, allows us to deal with this guy and with this guy. And this is due to equicontinuity. We have chosen delta such that it is yes. It
This is
should
our property exclamation mark.
yes. I have forgotten how to say this word in English, the exclamation, yes. Yes. Okay, so we have this inequality. Good. Now I have to go to next slide. May go there. Probably I will write down here. So since phi is piecewise constant, piecewise linear. So better to say since phi is linear between xk and xk minus 1 and xk, we have the following, that this difference f of x minus f of xk, not f, phi of x minus phi of xk minus 1, this absolute value. Let me make it a little bit. Okay. So this is also smaller than 3 epsilon over 5 for any x in this segment, xk minus 1, xk. Yes. Why do we need it? So we have this inequality. So this is smaller than this stuff. But in between, so for all intermediate points between these two, so inside the segment, we have the same inequality due to linearity of the function phi. So now I have to go to the next slide. May I?
Yes.
Okay, perfect.
Yes, please.
Yes. So now take any x in AB. Then there exists k. Let me write it down. K from 1 till n, such that this x belongs to one of the interval of partition, segment of partition. What do we have then? Then f of x minus phi of x is smaller or equal f of x minus f of x k minus 1, absolute value, plus absolute value f of x k minus 1 minus phi of x k minus 1, plus absolute value of phi. Let me shift it a little bit. Phi of x k minus 1 minus phi of x. Absolute value is closed. And then, yeah, due to equicontinuity, this is smaller than epsilon over 5. So let me first write down. So this is smaller than epsilon over 5 plus epsilon over 5 plus 3 epsilon over 5. So this is what we have just discussed on the previous slide. It should satisfy this inequality. And what is written here? This is equicontinuity, this condition. And this is so this is smaller than epsilon over 5 by the construction of phi. So probably let me use different color. So this is due to the construction. So this is the construction. Yeah. And this color, let me use this color to specify this. Okay, so finally we have this inequality. So this is exactly epsilon. And this means that such functions phi build an epsilon net for k. And the set of such functions phi is finite. So once again, these functions are piecewise linear functions with nodes in a given lattice. Lattice has finitely many nodes. So yeah, so that's why the amount of functions with continuous piecewise linear functions with such nodes in this lattice, they're only finitely many. Okay, and hence for any arbitrary epsilon, we have constructed a finite epsilon net for our set k, and hence k is totally bounded. Compact since it is also closed. Well, actually, this is the end of the proof. So you see, the proof is, well, purely technical, not difficult. standard argumentation from mathematical analysis. And the idea is, yes, so we show that from the conditions we have, we are able, so we have we have closed and bounded set plus some condition. And all these three assumptions allow us in total to show that the set is also totally bounded. That is allows us to construct an epsilon net for any arbitrary epsilon. Okay, so this is a standard strategy how one proves such type of theorems. So are there any questions to this theorem? Seemingly this is not perfect. Okay. So probably just one small remark. Or not, wait a minute. Yes. So look, so this is the theorem, so this is the equicontinuity. So I have reformulated how this definition looks like. So now I have rewritten in this way. So K is equicontinuous if for any epsilon we choose delta such that we have uniform continuity, which is uniform also with respect to F. So supremum over all F, supremum over all points x's prime and 2 prime, such that the distance between them is delta, no bigger than delta. And here we have this. Is it clear for you that this is the same reformulation, equivalent reformulation of what we have seen before?
Yes, yes.
Yes, okay, good. Also, just a small remark. So if we would have R instead of instead of segment AB, then this supremum can be rewritten in the following way. So recall that we are in this space with this supremum norm. So we actually can extract supremum norm here. So yes, instead of AB, we have now R. And then this could be rewritten the following way. Supremum over all H, absolute value H smaller than delta. And here, supremum norm of the function F, which is a shifted function, minus the function itself, supremum norm. Are you agreeing with this new notation? So like,
Yes, like often like the definition of the derivative is rewritten in this manner.
yes. So like x prime plus h, where h is smaller than delta. Using this, we rewrite this thing. So equicontinuity can be written this way. So supremum over f, supremum over these things. So, and then the norm of our space. And here the difference between our function and shifted function. But we shift a little bit. So this shift is not bigger than this delta. Okay, so this is just a small remark about different views of the same condition. And now let me discuss some further criteria, compactness criteria, and let me speak first about this space. So LP
But
space.
excuse me,
Yes.
like about the previous slide.
Yes.
But of course, like this theorem will not work the same.
Of course. Yes, it's a good
It's
remark.
just a definition.
Yes. So what I said, it was just about, so forget
Mhm,
about the theorem, just this supremum, if we would have R with, instead of compact set, this supremum could be rewritten this way. It was not about the theorem. But yes, if our theorem is not in AB, but on some non-compact set, then of course it is not enough. We need something more. And this is exactly what we will discuss. And now all the rest it will be just like how to say it, advanced material, not in the standard course, so we will not prove anything, but I will give you some references where you can find the proof, and we just, like, есть многое на свете, брат, горацию. So just let me introduce some ideas and concepts which are related to this compactness in different spaces, which are important. So that's why, first of all, I want to discuss the space LP, and you see here we don't have AB, we have RD. So we have two steps. Instead of compact set, we have RD, and instead of continuous functions, we have LP. So how to deal with this situation? So I will give you a quotation. Compactness in function spaces is usually characterized by conditions of the Arzelà-Ascali type. Typically, what is necessary is an equicontinuity condition with respect to the norm of the space under consideration. If the underlying topological space, this one, is not compact, then in addition, a tightness condition is required. Yeah, so if it is not compact, we need not only a kind of equicontinuity, but also a kind of tightness. What does mean tightness? Roughly speaking, tightness means that all functions or all elements of the set which we are considering have, roughly speaking, the same essential support. What does it mean? We will clarify in a minute. So this is the quotation of this source. It is something not very old, and there are a lot of references to other publications where you can find many different interesting things. But in particular here in this paper, you can find some compactness criteria in some more advanced function spaces. But nevertheless, so this is actually the idea. So we need a kind of equicontinuity, and we need a kind of tightness which allows to work in non-compact underlying space. Okay, so the theorem, so compactness criterion in this space. This is a theorem of which has the name. So some people call it Frische-Kolmogorov. Some people call it Kolmogorov-Riess-Weil theorem. So it looks as follows: a closed and bounded. So it is always the needed thing. So a closed and bounded subset K of this space. So for all P from 1 till infinity, including 1, but not infinity. So a given set K is compact if and only if the following conditions are satisfied. So equicontinuity with respect to the norm of this space. So for any epsilon, there exists delta such that supremum over all F in our set, and then supremum, so what we have already seen, but now the norm is different. Not supremum norm, but P norm. So this guy is smaller than epsilon. Okay, equicontinuity with respect to LP norm. And the second condition is tightness. So for any epsilon positive, there exists a compact set U in RD such that, roughly speaking, all elements F of our set K, they live, roughly speaking, almost in U. That is, if we consider the difference between the function F itself and the cutoff, that is, we have cutted off everything outside this compact set U. So this norm should be small for all elements F. This is exactly the idea that all elements of this set K, they are somehow, roughly speaking, essentially live here, and everything what is outside is, well, arbitrarily small. Okay, so this is just the statement and the idea. So what kind of conditions are needed to have a compactness criteria in function spaces? So now what about the proof? So Kolmogorov-Riess-Weil. So Weil, so this is this publication. And in this paper of Sudakov, there are a lot of comments on the original result and some subsequent more advanced results in this direction. In particular, there is also a list of references containing the original publication of Kolmogorov and original publication of Riess. So you're welcome to look. So this is available online, free available in English and in Russian. So you're welcome to look there. So for the proofs and further references. Okay, so you see equicontinuity and to fight with non-compactness of the guy, tightness. And again, tightness, what does mean tightness? It depends on the space where you are living in. But so the idea hopefully is clear from this statement. Moreover, what is important to know that in the case of L2, there is also one additional criterion of compactness. So remark 220. So if we are working in L2, it's a Hilbert space, and there is a nice thing, which is the Fourier transform. So do you know the Fourier transform or not? Yes?
Yes, I know.
Yes. Okay, so Fourier transform is very helpful instrument for many different things. So in this particular special case of this theorem, the equicontinuity condition, so this condition, is equivalent to the tightness condition for the Fourier transforms. So we have a set K. We consider all Fourier transforms of all elements of this set K. So we have another set, K hat. This is again a subset of L2 because Fourier transform maps L2 into L2. So equicontinuity for F is equivalent to a kind of tightness for F hat. That is, a closed and bounded set in L2 is compact if and only if both K and K hat are tight in L2. Okay. So this is the paper where you can find a proof. So of course, this is not anymore like a kind of everything is trivial and can be easily covered by standard lectures on functional analysis, but still you have the way how to find the proof. And so my task to show you the ideas, so concepts and ideas which are important. So please remember that equicontinuity is an important thing and tightness is also an important thing to get compactness in important spaces. And sometimes they are, so to say, dual if we are living here and work with Fourier transforms. Okay. So since we have already not that much time, I suggest.
Excuse me, but
Yes.
won't the Fourier transform transform our L2 space into a complex version of it?
Yes, we should work in complex,
Mhm.
so with functions taking complex values. Yes, yes.
Mhm.
So here we embed this space into L2 RT, taking values in so these guys will be functions of real argument, but taking complex values. Yes. Yes, that's true. So we can consider from originally think that this is such space. We have not yet discussed how to complexify Hilbert spaces. Probably we will do it next time, but yes, this is a question which we can discuss when we discuss Hilbert spaces. We have not yet done it, but yeah.
Thank you.
Okay, so, good. So further questions? Okay, similarly, it is not the case. So then, let me introduce one more important case, or one more important space, infinite dimensional space, which is important for applications. And let us discuss compactness criteria there. So this space is the space of measures. And now the literature, so the source where you can find all the proofs is this 2-volume book of Vladimir Bogachev, Measure Theory. There are 2 volumes. And what we will discuss now, it is chapter 8. This is volume number 2. Again, the book is available in English and Russian. And yeah, you're welcome to read it. This is really a monograph which contains all important things about measures. Okay, and again, there will be only slides because it is a kind of advanced material just for letting you know that there are such interesting things. So like a first introduction into the topic. Okay, so we consider so far, so now we will consider a complete separable metric space, not a big just abstract topological space, but just this particular case. So if we have a metric, then we can create a topology generated by this metric. Hence, we have a topological space, and hence we can consider the Borel sigma field or sigma algebra on this topological space. So by definition, this is the smallest sigma algebra which contains all open sets. So this is a sigma algebra or sigma field generated by this topology, all open sets. So in Russian and in German, people call it sigma algebra. So in English sources, it is called sigma field, but this is the same object. So this is the name of the question of how you name it. Okay, as soon as we have a sigma algebra, we may consider measures on this sigma algebra. So Borel measures, they are measures which are defined on the Borel sigma algebra. And we may consider even real valued measures, or sometimes people call it signed measures or charges. So this is the measures which may take also negative values. But as a subset of this space, we may consider probability measures. So probability measures will be denoted by P of X. So far, everything is clear.
Yes. Yes, yes.
Yes, we go further. Remark, so this space of all measures, so this space will be denoted as M of X, so the space of all real valued Borel measures on X, is actually a Banach space with a particular norm, which is called the variation norm or the total variation norm, and it is defined as follows. So if we have a real valued Borel measure on X, we can find its Han-Jordan decomposition. Do you know what the Han-Jordan decomposition of a signed measure is?
Yes.
Okay, only one person said yes, but okay, you can look in the internet what does it mean. But roughly speaking, if you have a nice signed or real valued Borel measure, then there are for this measure there is a set A, measurable set A in our set X, such that and there exist two measures, not negative, so standard measures, non-negative measures, such that how was this? Okay. Let me write down. There exists a set A in this Borel sigma algebra such that mu plus of A is equal to 0. So this is a 0 set with respect to mu plus, and mu minus of X minus A. So the complement of A, mu minus of complement of A is 0. That is this Han-Jordan decomposition says that we can decompose mu into two measures such that they are singular and such that both measures are non-negative. And then mu can be represented as this difference. So it's like a positive part of mu and negative part of mu. This is the same as we did with functions, where this is the maximum between f and 0, and this is something, yeah, so positive part and negative part. The same happens with measures. So we take a signed measure, we find its Han-Jordan decomposition. So we have two non-negative measures, and then we define this object. This is again a Borel measure, which is mu plus mu minus, not minus but plus, and this is a non-negative measure. And then we measure the value of X with respect to this total variation, and we obtain this object. So the statement is that this operation gives us a norm. And since we consider signed measures, so real valued measures, so this space is actually a vector space. That is a sum of two, or a linear combination of two real valued Borel measures is again a real valued Borel measure. So we have a vector space, and this guy is indeed a norm. So we have a normed space, and the statement is actually that this is a complete space. So it's a Banach space with this norm. Okay, so one can live in the sets of measures, in the spaces of measures, and do standard things because they are nice spaces. In particular, this guy with this norm is just a Banach space. Okay, is everything clear so far?
Yes.
Yes, yes.
We go further. Remark 2.22. So let tau1 and tau2 be two topologies on a given set X. If a topology tau2 is weaker than the topology tau1, then any tau1 convergence sequence converges in tau2. Is it obvious? What does mean that the sequence xn converges? Okay, probably. So xn converges to x, so in tau I. What does it mean? This means that for any neighborhood ux of this point x, so neighborhood in this in the given topology, for any open neighborhood of the point x in a given topology, there exists a number n, natural number, such that all xn belong to this neighborhood of x starting from this point. So the tail of the sequence belongs to any given, so for any given open neighborhood of this point x, we find the number starting from which the whole tail of the sequence lives in this neighborhood. Now, the more open sets we have, the more complicated it is for a sequence to satisfy this condition, yeah, because this is a condition for any open set. Agree?
Yes.
Yeah, so the idea is the stronger is topology, the more complicated it is for a sequence to converge. So there are fewer convergent sequences. So now if we want to have more convergent sequences, we need to find a weaker topology. Yeah, so this is so often the idea. So why we use functional analysis in applications. We have something, we want to approximate it, but by something reasonable. But if we consider something reasonable, it should converge in some sense. And usually, yeah, so we have to create this sense such that what we have converges in this sense. That's why the weaker convergence we consider, the more chances we have to construct something which converges in this weak sense. So it is a kind of motivation. So the idea is that, so this is a nice set with a nice, yes, if we have a norm, we have a distance and hence we have a topology, but this topology is rather strong and many interesting situations are not covered by this topology. However, many interesting things are covered, so it's an important example. But sometimes, in some cases, we need a weaker topology. So the set of all measures, Borel measures, can be endowed with the so-called weak topology, which is strictly weaker than the topology generated by the norm, by the variation norm. And this weak topology, we will discuss what does mean weak topology so within this course, but later on. So far, this is just the name, just the name of a topology, which is just weaker than the topology generated by this norm. And so far, it is enough to know about this topology that the convergence of a sequence in this topology, called weak topology, is given in the following way. So a sequence of elements of our space, we are in the space of all real valued Borel measures on X. So we take a sequence of measures and we say that the sequence converges weakly to a measure mu from the same space if for every bounded continuous real function f on X, we have this condition. So the sequence of measures mu n converges weakly to this measure mu if such integrals converge. So each integral is already a number, yeah? So it's a sequence, a scalar sequence of numbers. So we may say that here the set of all bounded continuous real functions f, this is a test set or set of test functions. So we test our measures against any element or any bounded continuous function, and so the result gives us something convergent. Okay, this is just a standard notation in many books. We don't use it so why in this lecture later on, but just to information. Okay, so this is the definition of weak convergence. So we know what does mean that a sequence of elements in our space converges in this sense, weak convergence. But from that one can restore the topology, the underlying topology. Remark, in the case of probability measures P of x, so this is a subset of this set. So if we focus only on this subset, then this convergence corresponds to the so-called convergence of distribution. Namely, if we have a sequence of measures, which are probability measures, this means that these are lows of some random variables. So we have lows of random variables psi n. So the convergence of this sequence of measures is equivalent to the convergence of the random variables psi n in distribution. So that's why this weak convergence, weak topology on the set of measures is very important. Okay, since I don't know, so you are all very different. Your knowledge, preliminary knowledge is very different. So somebody of you may know everything of it. Somebody may know nothing. That's why I will ask. So after each step, I will ask if there are questions, if everything is clear or not. So everything is clear so far?
Yes. Yeah, it's okay.
Yeah.
I worked with convergence of probability measures and eager to.
Yes. The question is that we have started later. May we continue? May we finish later? So maybe do 90 minutes as it was planned, or not?
For me, it's okay.
Okay. So anyway, everything is record. So if somebody has to leave, you're welcome to leave. Then the recording will be presented. Okay, so we go further. So we consider this space with a topology which is called weak topology. We don't know anything so far about this topology except that the convergence of sequences is given by this condition where we use bounded continuous real functions as test functions, so to say. Okay, remark. If our space X is separable metric space, then the space, so what does mean this symbol? This is a subspace of this space, not subspace, subset of this space. So this is a vector space. This is just a subset which contains all non-negative Borel measures. So the statement is that this subset of this space, endowed with the weak topology, is actually a separable set, and it is metrizable. So there is a metric which is called Kantarovich-Rubinstein metric. This is like a keyword. You can make your further investigations using this keyword. So there is a metric which allows to metrize the space, the set of non-negative Borel measures, endowed with weak topology. That is exactly this topology is metrizable with the help of a given metric. And again, so if our X is separable and metric, then this set is again separable and metric with this metric. So this is a good space. It's very easy to live there. In particular, if we have a separable and metric space, then you see that it will be written just, I guess, in a few next slides. if our separable metric space is additionally complete, and if we consider not only non-negative measures, but probability measures, again with the weak topology, then this space P of X is not only separable and metrizable, but it is also completely metrizable. That is, it is metrizable in a way that it becomes a complete metric space. This is the so-called Polish space. Such spaces are very often used in probability theory. So Polish space is a topological space whose topology is metrizable up to a complete metric space. Yeah, and separability is also included as a condition. Okay, in this super special case, there is also another metric, the so-called Levy-Prokhorov metric. So you can use both Levy-Prokhorov metric or Kantarovich-Rubinstein metric, and both of them correspond to the weak topology on this set. Okay, again, this is just a keyword. So some words which are like important keywords and which allow you to go further investigations. Okay, I guess no, it is not written there. But anyway, so we have when we see when we are here or here, in good cases, and this is exactly the case we consider, these spaces, they are metrizable and separable. So actually, to discuss the topology, it is enough to have convergence of sequences. We don't need nets, yeah, or dealing with neighborhoods. So it's enough to have convergence of sequences, so sequential convergence. Yeah. Okay. Yes, I have forgotten to mention that. Yeah. So here in brackets we use relative compactness. So compactness here relative, but I have already mentioned that a set is called relative compact or relatively compact if its closure is compact. So it's like criteria of total boundness, let's say like this. So after that, you may consider the closure of the set and get a compact set. Okay, so let us go further. In order to formulate the compactness criterion in this set, or in this set, or in this set, we need, again, a kind of equicontinuity or tightness or whatever. So that's why let us see what we need. So definition 224. A family M of Borel measures on a complete separable metric space. So we consider only this perfect case, complete separable metric space. A family is called uniformly tight if for every epsilon positive there exists a compact set K epsilon such that this holds. Again, roughly speaking, the supports of all measures in the family is more or less concentrated in this compact set. That is, what does it mean? We take this total variation measure, yeah, so the measure which was constructed from the Hahn-Jordan decomposition of the measure mu. So the idea is that there exists, for each epsilon, there exists a compact set in the Borel sigma algebra, so that so all measures are concentrated almost in this compact set. That is the measure, this total variation measure of all the rest is arbitrarily small. And this holds for all elements of our set. Yeah, so this is quite similar to what we have seen in the case of functions. What tightness means that the support, a function or a measure, support of all functions or measures in a family is more or less concentrated in the same set, and it is a nice set. That is a compact set.
I noticed that the naming here is pretty weird. Yeah, so when we talk about functions, the same property is called tightness, and with measures, it's called uniform tightness.
Well, you see, I have taken different sources for as sources. Yeah, so you make.
Well, I think I'm also familiar with this naming. So one is tight and one is uniformly tight.
But the idea is the same, yeah?
Yeah, but
Nonetheless, yes,
for some reason.
yeah. So thanks for the comment. Yes. So the problem is that also different authors may use different terminology. And so when the object or some theory becomes, so to say, classical, then there is a kind of established terminology that the majority of the scientific society use this terminology. Yeah, but sometimes there are different teams which use different terminology. So one should be careful what is actually meant. Yeah. Okay, so tightness. And one more thing which we need. So a family M of Borel measures on a complete separable metric space is called uniformly bounded if in the variation norm. Uniformly bounded in the variation norm if the following is true. Again, we use this total variation. So this is the norm, mu. So instead of equicontinuity, we have this uniform boundness. Yeah, so supremum over mu, this total variation, this is just mu, total variation norm of mu, it is bounded. Okay, so these are two definitions, and now the criteria. This is the very important theorem, which is called, named after Prokhorov theorem. So let X be a complete separable metric space, and let M be a subset of the set of real valued Borel measures on X. Then the following conditions are equivalent. Every sequence mu n in M contains a weakly convergent subsequence. And the second criteria, the second statement is that the family M is uniformly tight and uniformly bounded in the variation norm. Yeah, bounded in the variation norm. Okay, so every sequence contains a weakly convergent subsequence. This is a kind of a relative pre-compactness. Sequential relative compactness or sequential pre-compactness. I guess, yes, this is the remark. So Prokhorov's theorem gives a criterion of the weak sequential compactness. Yeah, so sequence, not net, but the sequence contains a weakly convergent subsequence. So sequential compactness of a set of Borel measures on a complete separable metric space X. If we consider not all measures, but non-negative measures only, this criterion is equivalent to the weak compactness without the word sequential, because we know that the weak topology on this set is metrizable, and hence the weak limit of a sequence of non-negative, and additionally, the weak limit of a sequence of non-negative Borel measures is itself a non-negative Borel measure. Of course, it is a separate statement which should be proved, but the idea is that so we are not able to prove so many things. Please read 2 volumes of the book of Bogachev. But once again, since we are in this case, we are in a separable metric space, then the sequential compactness is equivalent to compactness. So this is the thing. So in this case, which we consider complete separable metric space, and if we consider only non-negative measures, everything is fine. So this is really the theorem which gives us a criterion of weak compactness of the sequence, of a set. So weak compactness of a set is just uniform tightness and uniform boundness.
So this works well for probability measures.
Yeah. So this is a set which includes probability measures. Here we have non-negative measures, so probability measures in particular. But in general setting, so in the whole space, this is the statement of the theorem. So there is a small fine thing. So once again, so this is a nice vector space, which so where we can consider weak topology. But yeah, so we are interested in this space, so non-negative measures and particular probability measures. And it turns out that this subset of this space is a little bit nicer. There you can introduce this Prokhorov-Rubinstein metric. and make it a separable metric space. And then in this case, sequential stuff is equivalent to sequential compactness is equivalent to compactness. That is, we really don't need any net or neighborhoods. It's enough to deal with sequences. So for those who has sufficiently much preliminary knowledge, what I say is clear. If you see everything for the first time, it is too hard to get further. Just relax. It's just the first introduction, first meeting with this space. But this is an important space, this one and this one, in particular probability measures. So be aware. So for probability measures, this is the criteria of compactness. Okay, I guess there are just a few words left. So theorem 228. So a sequence mu n of probability measures on RD. So not in an abstract X, but on RD. So a very nice space. So a sequence of probability measures, yes, not just sign borrow measures, but probability measures on RD, converges weakly precisely when the sequence of their characteristic functionals converges at every point. And the function phi, which is a limit of characteristic functionals or Fourier transforms, yeah? So characteristic functional is the same as Fourier transform of the measure. Yes? Is it known or am I too fast? Should I introduce this? Please give me
For
feedback.
me, it's known.
So if somebody wants me to clarify this about Fourier transforms of measures and characteristic functionals, let me know. If there is silence,
Yes,
then
can you please clarify?
yes. Okay. So let me have a probability measure mu, which is a distribution of some random variable psi. So law of random variable psi. So in one hand, what is phi of x? It is the expectation of e to I x psi. So this is a characteristic function of the random variable psi, which we may, so by definition, what is it? It is ex, okay, omega, psi of omega, p d omega. So this is the integral. Expectation is the integral over the probability measure. Now we may use change of variables formula. So let me assume that psi is like a real valued random variable. So it will be integral over r, and here exy, and here will be distribution of psi dy. But this is just the Fourier transform of the measure p psi at the point y. So the Fourier transform of the measure is a function which is actually, yeah. So this is the definition of characteristic function of a random variable, but this can be defined not only for probability measures, but for all measures, such that this integral is
maybe p tilde in x.
Yes. Sorry, it's a typo. Yes, of course, in x, of course. We have integrate with respect to y, but yes, x will survive. Thanks.
So mu tilde is the same, but except p we have mu, yes?
So once again, we may consider Fourier transform of a measure. If we have a measure mu, then its Fourier transform is a function which is defined by e to the power I xy mu dy. And this can be defined, okay, let us assume that the measure is over R or over RD as here, yes. So this is the formula which defines the Fourier transform of a measure. Okay, it exists for measures such that this integral makes sense, or converge for all x's, in particular for all bounded measures. So, and hence as a special case, we have probability measures, and then we are back to this characteristic functional. Yes, but the Fourier transform of a measure, it is a notion which exists not only for probability measures, but yeah, for all bounded measures, in particular for all Borel real valued measures.
Okay, so thank you very much. So I'm sorry, I just never seen that notation that this is characteristic functionals. So it's the same characteristic transform of the measure and characteristic functional, or not?
Or characteristic function, probably. Not functional, but characteristic function. But have you ever seen characteristic function of a random variable?
Yes, yes.
Yeah, so this is it.
Just in your theorem, it's written characteristic functionals.
Again, this is a matter of notations. You may think about functions, but we have RD. Well, yeah. So okay, so this is the same object. So what is meant is the Fourier transform of a measure.
Okay.
I just want to remind what we have seen for compactness criteria in LP, so in L2 of RD. So there we said that Fourier transform is can be used to formulate a compactness criteria. So instead of equicontinuity, we may use tightness of Fourier transforms of functions. Here we have a kind of similar story, but instead of functions we have measures, but still measures have Fourier transforms. And for probability measures, it is the same as characteristic functions or functionals. So again, coming back to this theorem, it's a theorem of Levy. So a sequence of probability measures on RD, so probability measures, this is one thing, and RD is a special case of X, second thing. So a sequence converges weakly precisely when the sequence of their Fourier transforms or characteristic functions converges at every point, and the limit function, as I said, Fourier transform of a measure is a function. So the limit of these Fourier transforms is again a function, and it should be continuous at origin. If it is so, if it is the case, then phi is itself the characteristic function of a probability measure. That is the limit of the measures mu n in this weak topology. So let us read it quietly. Again, this is a compactness criteria in probability measures. So here, in particular case, X is equal to RD. So, and instead of tightness criteria, we may use a kind of continuity or equicontinuity or so you see, so this is the theorem. So compactness criteria. So the family is uniformly tight. The family of measures is uniformly tight and uniformly bounded. So if we work in this space of probability measures, then the whole set is bounded, uniformly bounded. Yeah, all probability measures satisfy this condition, or I can say like this. Yeah. So P of X is uniformly bounded, so we can forget about it. So in the set of probability measures, what is interesting for us, it is this condition. So the statement is that in this special case of RD and probability measures, instead of considering uniform tightness of this set, we may consider, and yes, if we consider not just a set, but just a sequence. So the set is just a sequence. So instead of uniform tightness, one may consider characteristic functionals or Fourier transforms of these measures. And so the criteria is that the sequence of characteristic functions converges at every point, and the limit function is continuous at the origin. If it is so, then this limit function is itself a characteristic function of a probability measure. And this probability measure is exactly the limit of this sequence of measures in the weak topology. So again, Fourier transforms are very important. Okay, and so the second statement of the Levy theorem is as follows. So a family M, so not just a sequence, but just some family of probability measures on RD is uniformly tight if and only if the family of its Fourier transforms is uniformly equicontinuous on Rd. But this uniform equicontinuous on the whole Rd is enough, is equivalent to the uniform equicontinuity just at the origin. Yes, because exponential function is a special function and very special function. So here, all characteristic functionals, they have a special structure, so to say. So really here, we need only continuity at the origin. Okay, this is just, again, we are not going to prove anything. This is just for you to be aware that the things which are really important in the context of compactness criteria in important spaces, they are like tightness, equicontinuity, and Fourier transforms are also important. And sometimes you play with all of them to get different compactness criteria in different spaces. Okay, now the last slide for today. Proposition. So let X be a compact metric space, then the set of probability measures on X is itself a compact set in the weak topology. This is also an important result. So you see the set of probability measures is a very nice set. So if X is a complete metric, a separable metric space, then this guy is a Polish space. That is, again, a complete separable metric space with, for example, Levy-Prokhorov metric. But also if X is compact, then the whole space of probability measures is compact in this topology. That's why, again, this is an important topology. Okay, conclusion. So in applications, one has to work with different non-trivial spaces of functions or spaces of measures. There exist different criteria of compactness in these spaces. So in applications, it is often convenient to have sufficiently weak topology where the objects which are interesting for us may be approximated by some nice things, and these nice things would converge in this sufficiently weak topology. So we are interested in sufficiently weak topologies. The one is presented now here for measures, weak convergence and weak topology for measures. The general construction of weak topology will be discussed later on during the course. So yeah, in the context of function spaces or spaces of measures, remember that tightness, equicontinuity, and Fourier transforms are important notions which help with compactness criteria, with convergence, and so on. Okay, so I think that the topic compactness is finished. Now, if you have questions, you are welcome to ask them. Or if you are shy, we can stop the recording and then you ask your questions. And then next time we start with the new topic concerning normed and inner product spaces. Okay, other questions? Or remarks or
Yes.
comments? Yes, please.
First about the notion. When we say Fourier measure, do we
Can you repeat, please? I heard only a part of your speech.
okay. When we say Fourier measure,
Yes.
do we assume that this measure is finite or not?
Yes, when we deal with signed measure and Hahn-Jordan decomposition and a Banach space with a total variation norm, yes. Yeah, so we assume that the measures are finite, yes.
Thank you.
Otherwise,
second,
yeah. Yes, so this mu of X, this is the norm of the measure mu, and it should be finite. So if our measure is non-negative, this means that this should be finite. So the measure is finite. If the sign measure is decomposed into two parts. Sorry, minus. Yes, but then so mu is equal to this Han-Jordan decomposition. Then we construct this mu absolute value. This is mu plus mu minus, and this is a non-negative measure, and we assume this. And we consider this set, but now with another topology, a weaker topology. Yeah, so the measures are finite.
Okay, thank you. And also, one characteristic function, why the property at the orange is so uh, important. Could you please just say a few words?
Um, So I think so. Let me first prepare the answer to make it so to make it compact and reasonable. I understand. So we are discussing this story. So characteristic functional looks as follows. So here we have random variables. So we have like this, something like this. So let me answer next time, because now I will probably it will take a lot of time and it will be chaotic if I start just to answer without preliminary thinking about it. So I
No
will
problem.
answer the
Thank you.
question
Thank you.
why we need only a region here. So why or here why only the origin is important. Yes, we will.
Yeah.
Yes,
Okay.
yes,
Okay, thank you.
yes. I will answer. I would say so. It is related to the following property of exponential function, that e. Let me call it, okay, 1 over n t. It is the same as e to the power t to the 1 over n. Yeah, so this this property is makes the deal, but let me prepare the answer to make it sufficiently fast and clear. Yeah, so when n tends to infinity, then here everything tends to 0, this argument, yes?
Yes.
And here we have a kind of power, but let me, so probability measures again, yeah, so let me answer next time, but I will remember the question.
No problem. Thank you.
Welcome. So some further questions? Okay, it seems that there are no more questions. So let us hope that we will meet on Friday this week in Zoom. Once again, if something is wrong with Zoom, then you check your email and I will send some instructions what to do. Probably we shift the lecture, or I don't know. Anyway, if you have some ideas on what can we do instead of Zoom, you're welcome to write me an email about that.